Hey there, welcome back to the next section, Hierarchical Clustering. Here we're first going to look at hierarchical strategies, then we'll look at agglomerative clustering, and finally we'll look at the connectivity constraints. Now we move on to the first video of this section, Agglomerative Clustering. In this video we're going to take a look at hierarchical clustering, then we'll learn about agglomerative clustering, and finally look at dendrograms. Hierarchical clustering is based on the general concept of finding a hierarchy of partial clusters, built using either a bottom-up or top-down approach. More formally, they're called agglomerative clustering and divisive clustering. Agglomerative clustering. The process starts from the bottom and proceeds by merging the clusters until a stop criterion is reached. In general, the target has a sufficiently small number of clusters at the end of the process. Divisive clustering. In this case, the initial state is a single cluster with all samples, and the process proceeds by splitting the intermediate cluster until all elements are separated. At this point, the process continues with an aggregation criterion based on the dissimilarity between elements. Scikit-learn implements only the agglomerative clustering. So let's learn more about it. Consider this dataset. We define affinity, a metric function of two arguments with the same dimensionality, m. The most common metrics are Euclidean, or L2, Manhattan, or L1, and cosine distance. The Euclidean distance is normally a good choice, but sometimes it's useful to have a metric whose difference with the Euclidean one gets larger and larger. The Manhattan metric has this property. To show it, in the figure, there's a plot representing the distances from the origin of points belonging to the line y equals x. Once a metric has been chosen, the next step is defining a strategy, also called linkage, to aggregate different clusters. There are many possible methods, but Scikit-learn supports the three most common ones. Complete linkage. For each pair of clusters, the algorithm computes and merges them to minimize the maximum distance between the clusters as shown. Average linkage. It's similar to complete linkage, but in this case the algorithm uses the average distance between the pairs of clusters as shown. And last one is wards linkage. In this method, all clusters are considered, and the algorithm computes the sum of squared distances within the clusters, and merges them to minimize it. From a statistical viewpoint, the process of agglomeration leads to a reduction in the variance of each resulting cluster. The measure is the wards linkage supports only the Euclidean distance. It's better to understand the agglomeration process. It's useful to introduce a graphical method called a dendrogram, which shows in a static way how the aggregations are performed, starting from the bottom to the top. Unfortunately, Scikit-learn doesn't support them. However, SciPy provides some useful built-in functions. Let's start by creating a dummy dataset. The code is explanatory. Running it, we get this scatter plot. To avoid excessive complexity in the resulting plot, I've kept the number of samples very low. Now we can compute the dendrogram. The first step is computing a distance matrix. We've chosen a Euclidean metric, which is the most suitable in this case. At this point, it's necessary to decide which linkage we want. So we import it, and we take ward method. However, all known methods are supported. Now, it's possible to create and visualize a dendrogram. So we import dendrogram and add this code to plot it. Run the code, and we'll get this plot. In the x-axis, there are samples, while the y-axis represents a distance. Every arch connects two clusters that are merged together by the algorithm. For example, 16 and 18 are single elements merged together. The element 22 is then aggregated to the resulting cluster, and so the process continues. As you can see, if we decide to cut the graph at a distance of 10, we get two separate clusters. The first one from 15 to 24, and the other one from 0 to 20. Looking at the previous dataset plot, all the points with y less than 10 are considered to be part of the first cluster, while the others belong into the second cluster. If we increase the distance, the linkage becomes very aggressive, and with values greater than 27, only one cluster is generated.